应该大家都 see the here, right?
Oh,
Yeah,
maybe I can also put
yeah.
up there. Or whatever you think is better.
I think maybe here. Okay. Okay. Thanks. Yes.
Okay.
Okay.
You are seeing the screen? Yeah.
Yes.
Okay. Hello, everyone. Thank you for coming to the talk. It is absolutely my pleasure to introduce to you Fanghui. We will be giving the talk today. With Fanghui, we have been working together for quite some time. Currently, he's a professor in University of Warwick in the United Kingdom. Before that, we were both in EPFL group in Switzerland. And Fanghui has also done some work previously in his PhD. He has studied in China in his during his PhD, and then also was in the famous University of KU Leuven. And I believe today he will be talking about some very interesting topics on robust overfitting, which is like a very big problem in robustness robustness of deep learning models. And he will focus today in the topic from a very theoretical standpoint. Thank you very much for coming once again, and Fanghui, stage is yours.
Okay. Thanks for Piper's nice introduction, and thanks for your time. And okay, let me start. So today the talk is about the robust overfitting. So we're interested in that, okay, whether robust overfitting exists in theoretical sites. Okay. So today's talk is mainly focused on the approximation review. So, and firstly, so I already know that so the deep neural networks actually are normally working the over parameterized regime. That means the number of the parameters is much larger than the number of the trained data. The typical example includes the resonance, transformer, and also recently very important model. So we can see that in the past 10 years, the machine learning model becomes larger and larger. And because of over parameterization, the deep neural networks have already achieved very promising performance. For example, they can fit the noisy data. Sorry, they can fit the true label or random label. So that means the model is very complex to fit the random labels. And besides, the deep neural network can not only to achieve the zero error for this noisy data, but also can achieve very low the text risk. So that means the deep neural networks can perform well. So this is called binary fitting. So here I use a general version or general the concept of binary fitting. So if the model can fit the noisy data with zero training error, with small training error, and generalize well, so we see that this is called binary fitting. Okay. And about the deep neural network training, we often focus on the classical empirical risk minimization. So we want to evaluate the difference of the neural network outputs, FW. W is the parameter of the neural networks, and also Y is the label based on this training data. Okay, so we are interested in, okay, how does the estimator F hat can perform well or not on the new data. And here we consider all the possible estimator is in a function space F. So in our talk, so we have to think about this is a deep ReLU neural network. So you have air layers, and at each layer, okay, you have the weights. Okay. And we already mentioned that, okay, the deep neural networks is good at fitting the data and also fitting the noise. So this will lead to a significant issue in robustness. So even though the neural networks is well trained, can achieve very good performance, if the input data suffer from some small modifications and the outputs, sometimes will change a lot. So this leads to high risk if you want to build a robust, secure, trustworthy machine learning system, right? So if we want to improve the robustness, the typical method is the adversarial training. So instead of just to fit the only one data points, we are interested to consider all the possible data around the original data X. So we are considering the perturbation ball. And in this case, we introduce the additional max optimization in the empirical risk minimization. Okay. So this is called the worst case robustness because we are considering all the possible data around the X-side. Okay. So it have already achieved good performance practice, and here is the famous results on the multiple layer the neural networks on the CVPR data set. So we can see that the red curve is the standard training error. So okay, it can be close to 0. And also for the robust training error, it can be also close to 0. So that means for neural networks, even though we are want to do this min-max optimization, it can still achieve the 0 training error or close to the 0 training error. So that means it can still overfit the high dimension ball. Okay. But for test risk or test error, so we can see that. So for the robust test error, this blue curve, so we can see that the error actually increased when we want to overfit the perturbed data. So this is called robust overfitting. So when we overfit on the advanced failure of the training data, but it's true, it's sometimes we will harm the robust generation. Okay. So there is another finding is okay about the gap. The gap between the clean accuracy or robust accuracy or clean the standard training error or the robust generalization error. The standard generalization error and the robust generalization error. So we can find the gap is large. Okay, and this is the typical observations from the experiments. There is another formula is called the robust accuracy trade-off, but this is beyond today's talk. So today's talk we are mainly focused on these two things. So whether the robust overfitting exists or not, how can we to avoid this in theoretical sites, and also how can we to understand the robust generation gap. Okay. So before we talk about our results, we need to think about this question. Can we avoid robust overfitting? Oh, go ahead. Okay.
So like if I add more information, I might go talk about image and the non-adversarial.
You mean this is just for the CVPR results?
Like the
Test. Okay.
Oh, it's all theoretical.
This.
Yeah.
This is empirical results. Okay. Yeah. On the CVPR and the perturbed the radius is 8 over. No. Okay. Okay, so here firstly I introduce the negative results. So for adding the two absolute separated data, sorry, okay, maybe I need to sit because I want to write something. Okay. So formal we have two data sets, A and B. Okay. We will assume formal it have the n data points, x1, x2, and xn. Okay. And B also have another data set, maybe it's z1, z2, and zm. Okay. And the epsilons separated means that, okay, for any possible, the I is from N and the J is from M, the index. Okay. And the distance between the xi and is zj. Okay. In the R infinite norm. Okay. So this is is larger than the epsilon. Okay, so this is called the separated. So you can think about, okay, we have two sides, this is A and this is B, and this is the epsilon. Okay, so this is not show that, okay, for any two separated data sets, okay, if we want to neural networks, to a deep ReLU neural networks, want to separate, okay, these two class A and B, and the required parameters is at least in the exponential order of the input dimension D. So what does it mean? That means that, okay, if the epsilon is sufficiently small, actually the requires the number of parameters are suffer from the cursor diversity. If the epsilon is large, if the epsilon is from 1, okay, this is nice, right? But definitely, actually, if the epsilon is 1, actually, this is too large. This is not realistic. So we're interested in, okay, how is this epsilon in practice? Okay. So this is the previous empirical observations on the different data sets. So here we can take the Sierra 10 as the example. And they are interesting, okay, for different class, maybe in the training data sets, or in the test data sets, and also training data sets. For this is class 1, class 2. Okay, so I'm interested in what's their distance. Okay. And their results show that, okay, for the training data sets, the minimal separation distance from this is class 1, class 2, this is class 1, class 3, and we're interested in what's the minimal separation distance. And they show that, okay, the minimal distance is 0.2. Okay. This is much larger than the typical perturbation radius. The epsilon they take is 0.031. So if you are familiar with the robust advanced train, so this is exact the 8 over 255. Okay. So in theory, so we can see that, okay, in practice, we use the perturbation radius actually is much smaller than the separation distance, whatever in the training data or in the training and test data. Okay. So that means, okay, the perturbation is actually much smaller than the well-separated data distance, right? But why we still will face on the cursor dimension T or the robust overfitting? So the question is, okay, we have already the well-separated data. Under which condition we can avoid the robust overfitting? So this is the main question of today's talk. Okay. So we want to understand this question from the typical, this is the typical framework in the deep learning theory. So firstly, we want to study the approximation. Okay. And then the generalization and then optimization. Okay. So for optimization, so I can give example to show that, okay, if we have two solutions, one is from the standard solution, okay, and one is a robust solution, okay. The approximation means that, okay, if we want to obtain a robust solution, maybe we require more parameters to approximate it, okay. For generalization means that, okay, maybe we require the order of the parameter to approximate, but the sample complexity will be larger. We require more samples to learn the robust solution when compared to a clean solution or standard solution. Okay, this is from generalization. Okay. And for the optimization is okay. Maybe they have the same for the sample complexity, but maybe okay, about the robust solution will require more time to learn it. Okay, so this is from optimization, generalization to optimization. And this also called statistically and also computationally. And in my today's talk, I will mainly focus on the optimization and also the generalization. Okay, even though this is the machine learning optimization seminar, but I will not focus on optimization. Okay, because actually optimization is too difficult for understanding the deep neural networks. Okay, so we actually the proof is based on the construction. So it means that, okay, even though we know the target function, okay, we know the ground truth, and then we construct the neural network, and then to see that what's the difference or the separation between these two solutions. And we can see that this construction is optimal. That means even though you know the target function, you still will have the gap or not, right? And then we have to see that whether we can avoid the robust overfitting or not. So this is why we say we have to want to understand the fundamental limits on robust overfitting. Okay, so in the next step, we have to talk some boring mathematics, notation, the heavy things. Okay, so in statistical learning theory, okay, so we focus on the regression. Okay, so actually in our work, we also give the results on the classification. Actually, this is more interested in the robust overfitting or the adversarial training results. But why we focus on regression? Because the main reason is the regression results actually is more easier to understand. And also this is the first step to give the analysis for the classification. So in today's talk, I'll only give the results about the regression. Okay. So based on the empirical risk minimization, and then we choose the L2, the squared loss. Okay, and then we do the regression. And for the data point, we consider the X is from 0 to 1, and in the RD space, and the label is in a bounded the domain from -m to f. Okay. Oh, okay. You see, it's not very robust. Okay, so we want to, okay, we obtain the f hat. Okay, this is our estimator, and we are interested in the generation. Okay, so we understand it from approximation view. So we have the target function f0. Okay, it can achieve the lowest the expected risk. Okay, it's defined as x and y is sum from a distribution rho. Okay, even though this is unknown. Okay, and then we are interested in what's the relationship between the f hat and also f rho. Okay, so this is the definition about the excess risk to describe this as the generalization. Okay, and interestingly, if we use the squared loss, this excess risk is equivalent to we directly consider the difference between these two estimator in the certain the L2 space, but the measure is the distribution zone. Okay, so sometimes we go directly to write it as to describe the generalization. So this is the reason why I say we understand it from the approximation view, because this is exact our generation performance. And if we consider the adversarial training, so we can do similar to define the from the empirical adversarial risk minimization. So we include the max over all the possible data here, and we can also to define the robust target function and over the robust expected risk. Okay. And about the robust excess risk is also similar to the standard excess risk. Okay, but here we see that, so we cannot write it in some certain L2 space, because we will introduce the maximum is we will destroy the structure. Okay, so our main question is, okay, so how can we to give the estimation of this robust X risk, and also what's the relationship between this and also the standard generation error with the excess risk? Okay, so this is a brief introduction about the statistical learning theory, and in the next, I will introduce some of the assumptions. This will be required for our theoretical results. So the first is about the source condition. So you can regard it, okay, we need to give some assumptions about the target function, right? So you can regard it, okay, so we assume that the target function f0 is alpha Holder smoothness. So alpha is controls the smoothness level. So if alpha is larger, you can see that, okay, the target function is smooth. So for example, okay, we have if you remember, we have two data sets, right? A and B, and there's a distance is epsilon, right? If this is the target function, okay, it's sufficiently smooth, right? And if it's quite from the non-smooth or something like this, so definitely we know that, okay, these two cases will definitely have different results, right? So this is reason why we consider the certain smoothness condition about the target function. Okay, about in the alpha Holder, the continuous function space, the norm is also related to the F infinite norm and also with the semi-norm. And this semi-norm you can regard it to some the similar the Lipschitz constants. So if alpha is 0, alpha is 1 is close to the Lipschitz constant. Okay, so you can think this is a generalized version of the Lipschitz constant. Okay, so this is the first assumption. So this is very standard and typical in the, okay, go ahead.
So you have like both F subscript W alpha infinity on both sides? So
sorry, yeah, this is table. Yeah, actually this is semi-norm. So yeah, okay. And the second assumption is, okay, we want to give some condition or constraints on the marginal distribution rho X. So the marginal distribution means, okay, we XY is sampled from a distribution rho, right? This is a joint distribution or the data X and also label. And the marginal distribution is only related to the data X. Okay. So we assume that, okay, the marginal distribution have the bounded supports. So what does this mean? This means that, okay, we want to show that we have the two function space, the L1 space, the L1 D rho. Rho X is our the marginal distribution. We want to show that these two function space are equivalent or consistent. So you can directly exchange these two function space. But definitely, yeah, if for any the distribution rho X, this is definitely not true. Only under some certain conditions, from rho X have bounded supports, we can to exchange these two function spaces. Okay, and from if the target function, if the rho X is a uniform distribution, or if some have some bounded, okay, this is definitely satisfied. But it's true that for Gaussian distribution, it doesn't hold because the Gaussian distribution have the infinite the support value. Okay. So this is our assumptions. We only require these two assumptions. So one is about the target function, one is about the rho X. Okay. Go ahead.
X is your data, right? Like
Yeah. So you can.
also bounded, right?
Yeah. Actually, you can regard this as a subset of our
Bounded
design.
subset.
Yeah. And also our data is considered in the 0 to 1.
Oh,
Okay. And in the next, I will to introduce a very famous the results in approximation theory, the cause of separation distance. So if you remember, we see, okay, the two data sets, A and B, have the epsilon the separation distance. And then we can give that, okay, the separation distance have a upper bound. Okay. So from we have the n data sets and n data, and it's in the 0 to 1, the RD space. And the minimal the distance between the xi and xj, if they are different, and then it can be upper bounded by n up to 1 over d. And these results can be proved by using the covering number. Okay, so intuitively, we have to see that, okay, the separation distance have a upper bounds. And that means, okay, for our the perturbed, the perturbation, the radius is normally it should be smaller than the qx, right? Otherwise, it will be meaningless. From that means that there are two data points. If you consider a very large perturbed, okay, the xi will become to xj. And then you say, okay, if we still want to pursue the robustness, it will definitely hurt your Kerning accuracy. Okay, so this is reason why normally we consider the delta is smaller than the qx. Okay, go ahead.
a dumb question, but this rho of x, this measure, whatever, right? If the
Yeah.
measure is defined on a bounded domain, why do you need this assumption that rho of x has bounded support?
So you mean why would you care this assumption?
Yeah, why isn't that assumption already there, given the fact that x, big X is just a sub, just.
Just in the 0 to 1?
Yeah.
Yeah,
so
yeah.
Why do you need that extra assumption?
Because this is a good question. Yeah. No. I think this is because this is a more general version because this is why I included this. Okay. Yeah, we can directly say, okay, we consider the supports is over the 1 to 1, 0 to 1. Okay. Yeah, but this is a more general version. Yeah. Okay. So this is the reason why we include this. Yeah.
All I'm saying is if X, if capital X.
Yeah,
is
yeah.
already a bounded
Yes.
domain,
Yeah.
why do you need-
Yeah. And actually, another reason I can also tell you that in our work, we don't use this assumption. We to use, okay, we introduce two identity mapping, and this identity mapping is bounded. So okay, one example is, okay, if it have the bounded supports, okay, this is true. But this will also cover our thing from forward. So okay, this is not a necessary and sufficient condition. Okay, but why I put it here is for the ease of understanding.
Okay.
Yeah, because if I have to say, okay, the J row are bounded, okay, I need to introduce what is the operator. Yeah, okay. Okay, so in the next, I can give our results. So it appears very mathematics heavy, but let me try to explain this. So, okay, so we assume the target function is in the Holder space, and the rho x is have the bounded force. Okay, this is our assumption. And the delta is our the perturbed radius. Okay, it's smaller than the qx. Okay, this is one, but it's divided by 3. And then this is also another additional term. So this is monotonic the function of alpha. So this is from 2 over d and to 1 over d. Okay. So the qx is smaller than the 1 over d. So you can think about they are always in the same order. Okay. And then there exists over parameterized deep neural networks, and it's depth and also width. Now we can see that the width, the first layer will requires in the n by d parameters, and for the remaining it's also in the logarithmic order of n. And then we can just see that, okay, for this neural network, we can give this generalization of the excess risk results, which show that for all the possible, the distribution rho x, and it can be upper bounded by the n up to the minus 2 alpha and up to alpha plus d. The alpha is describe the smoothness level of the target function. Okay. So firstly, we see these results. So we can see that the weights we require is in the n by d, the parameter. That means the linear over parameterization is enough. We don't require is large enough. Okay. And if you are familiar with bank results, I think it's in Neuronib's 2021. There's a best paper award to show that if we want to smoothly interpolate the training data, the required parameters is also at least the n by d order, but this is lower bounds. So you can see that, okay, even though they are only focused on 2 neural networks and this is deep neural networks, but if we think about, okay, 2 neural networks, well, we also require the form of the parameters is in the n by d order. So actually you can, in this case, you can just see that if you want to interpolate the training data, whatever you have, you are working the standard training or lower third training, the n by d is enough. Okay, so this is one thing. Okay, and another thing is, in approximation theory, also in the information theory, I think this is a classic result to show that, okay, in Holder space, the optimal rates of convergence by any learning algorithms, the optimal rates it can be achieved is in this rates. So you can see that the rates are matches. Okay, even though we don't consider logarithmic order. So you can see that our construction is optimal because we can achieve this optimal rates of convergence. Okay, even though our construction will based on the target function f so. Okay. So any questions? Okay. So this is about the standard. Okay, I also have some remark, but I think I have already to explain this. So we have already talked about the standard generation error, and our main results is about the robust overfitting, the robust generation error. Okay. So this is our robust generation. No, this is robust excess risk, the definition. So F and F so delta. And we can split it into 2 terms. Okay, the first term and second term. So the second term is directly the excess risk of the F, right? So this is to describe the generation performance of this estimator. So this is clean accuracy. Okay. And the first term, okay, this is the generation error of the estimator F. And this is the robust generation error. And this is the clean, the generation error. Okay. So actually this is to describe the robust generation gap, if you are familiar with this, when we mentioned before. Okay. So we can split the robust overfitting or the robust generation error or robust excess risk into robust generation error and also the robust, and also the clean, the excess risk. Okay, and our target want to bound these 2 terms. Okay, go ahead.
So on the left-hand side, the rightmost term.
Yes.
the others, before the end block, is that
Yeah.
typo or something, or what? I'm not seeing how this decomposes stuff.
No, this is not typo, yeah.
What's the epsilon to the power delta, the power delta stuff?
Okay. So here we introduce, let me see. One, and also we are plus F delta, F rho, and what's this? So, sorry. Something like this. Okay. And we also need to do the delta minus third. That's delta of those. So and we need to use two effects. One is as any f is smaller than any. Okay.
Oh, okay.
Right.
This is some intermediate steps.
Yeah, exactly.
Sorry.
Oh,
Just,
Okay. So this is our results. So this is the same assumption, but we will require the alpha is larger than 2. Okay. And we can see that delta is smaller, larger than the QX, and also is up to 1 minus by d plus 1. So this actually you can do also to think about this. So 1 is 1 over d minus 1, and 1 is 1 over d. So in practice, from how the image data, from how this d is about 700, 1000, or even larger, right? So these two values are almost the same, right? So you can do direct thing over delta directly smaller than the QX intuitively. Okay. So there exists, okay, we can construct the neural network, okay, and about the width and depth, okay, we are more care about, okay, how many the parameters they have. So we have to show that have the n by d plus additional term, and this will relate to the smoothness level about the target function, right? Okay, so we can prove that, okay, so for this construction over the neural networks can achieve the the adversarial training error. That means it can overfit it on the adversarial training data. And also the generation error is small. So it's by the square root of d and also delta. Okay. And if we do think about the delta is in between these two terms, okay, and then we can also give the robust acceptance risk, but it's true that this results is not very clear. Okay. And also I mentioned that, okay, this quantity and also the n up to minus 1 over d, actually they are very close if the d is large enough. Okay, so we mainly focus on this case. Okay. So let me to summarize the difference between the standard generalization and also the robust generation. Okay, so this is our result. Here I summarize this. So the parameters, so we can to see that, okay, we require a small parameter, but the upper bound is different. So, okay, so we need to compare them, right? Okay, so firstly, we only see the robust generation intuitively. So if alpha is larger, that means the target function is smaller. Is more smooth. And then we require the less parameters. Okay, this makes sense. Okay. And secondly, so we always require the perturb, the radius is smaller than this QX, the separation distance. So somehow if we consider a small enough, it takes a 1 over n rates. So in this case, we can to see that, okay, the upper bound will become the 1 over n. Okay, this is good. If we don't consider square root d. Okay. And for the parameters, what we have is will be the n by d and plus, if we take the n here, is d, 2 alpha minus 2, and also log n. Okay. If we don't consider the log n, okay, we can use the tilt. Okay. So we can see these results. Okay, I also to write it clear. Okay. N up to d over 2 alpha minus 2. Okay. So if the target function is not very smooth, from the alpha is in a constant order, it's not depends on d. So that means we require sometimes around n over d order the parameters, right? That means this will suffer some cursor dimensionality. So that means we require the target function is smooth enough, and then we can avoid the parameters is something. From if the alpha from is d, okay, so this is directly from in the is smaller than in directly in the n by d order, right? Because this is smaller than n. Okay, so that means okay, we require the target function is smooth enough. So now we can conclude our result to show that for the well-separated data, okay, because we are based on the separation distance, okay, the well-separated data, and also if the target function is smooth enough, that means alpha is large enough, and also the perturbation is small enough, right? So the delta is small, and then we can avoid the robust overfitting. Okay, go ahead.
Okay, so in practice though, this assumption withholder that you had before
Yes.
on the smoothness is
Yeah.
not followed in any of the networks, right? ResNet 18 doesn't have it, transformers don't have it, and so on and so forth, right? So
Wait. So actually, you don't know what's the target function of the amnes.
so putting the assumption on something you don't know is very
Yeah.
restrictive, right?
But this is more general. I can tell you why it's general. We don't know the target function of the amnes, CVPR or ImageNet. Okay, but we know that this function will definitely have some smoothness level, even though we don't know which smoothness level you have, right? The most simple way is, okay, we assume the target function is smooth. Okay. And then actually the function space is in a, can be described by the kernel methods is RKHS, if you are familiar with the kernel methods and RKHS. And you have to think, okay, why we need to assume the target function is smooth? Maybe you are thinking, this is too strict. We can to relax it. Okay, we consider the more non-smoothness level from what we can consider is in the holder space. So so that means the target function is only required the holder continuous. Okay. And then you can just say, okay, if alpha is large enough, okay, it's very smooth. If alpha is small, it can allow for some non-smoothness. Okay, you can also consider the more general or more larger function space from the basal space. You can allow for a lot of weird from the jumping, or spiking, the singular. Okay, but this is ESG, yeah. Okay, but I think normally holder space is enough for analysis.
So let me follow up and reverse the question.
Okay.
So well-separated data we can have, right?
Yes.
CVPR we
Yeah,
have,
Okay.
and that's where most people are
Yes.
doing the robust training.
Yes.
Perturbation is small enough is also true, right? People are using in practice 8 or 16.
I'm not sure this is small enough because I will also do the next pages.
Oh yeah.
Okay.
But even so, basically this
From
means-
this order, the 1 over n. Okay. From in practice, the data is from more than 50,000 or something like this. This should be sufficient.
Okay, so you mean that they're not the perturbation?
Yeah.
So for your last condition to be true, the perturbation needs to be almost 0.
Yeah. No. It can be not depends on the input dimension d. So this is large. This is small because this is a 1 over n. Okay. So if you say, okay, if the delta is small, here means it's not independent of d. Okay, you can say this is small. Okay, small enough. Okay.
Okay, so in practice we cannot have we need too small perturbation.
Yes. And also the target function is smooth enough. I think yeah, it's true that in practice we don't know how smooth is of the target function. But I can tell you that okay, it will depend on the smoothness level of the target function. Yeah. And intuitively you can also think about okay, for amnes and also the CVPR, maybe the target function in the CVPR is less smoothness than the less smooth than the on the amnes. Okay, in some intuitive. Okay. So now we also need to compare, okay, what's the standard generation and also the robust generation results. Okay, so here we to take the data, okay, at this rate, so we can do control the upper bound is the same. Okay, and here we also need to mention that, okay, in our the robust generation results, we require alpha is larger than 2, and then we check this condition is satisfied this. Okay, so we can directly see, okay, it's satisfied this, so we can compare this robust generation results and the standard generation results under the same upper bounds. So we can see the parameters. Okay, we can see that it's true that when compared to the standard training, which requires more parameters. Okay, so these are our additional parameters. Okay, plus some additional term. And this is related to the smoothness level of the target function. Right. Okay, go ahead.
I'm curious, did you verify it empirically that, for example, like the SGD for a synthetic data set will converge to the solution where the robust generalization gap is small?
Because this talk this work, we only focus on the approximation and the generalization. So the solution from the hats, we construct it by the target function. So we don't use from the SGD or gradient descent to train it. So this is different. But it's true that we can verify by this construction. We are definitely satisfy this.
Okay.
Because yeah, we prove by construction. Okay.
Do you know if the number of parameters for robust generalization is height or not? Or...
Good question. This is my next slides. Yeah. Okay. So here we can just say that I will answer you in the next slides. Okay. So here we see that we require the additional parameters, and this function is if I remember, this is a decreasing function of alpha. Okay. So if alpha is takes to 2, okay, this is we require the most. So normally if 2 is around 2, 4 plus d. Also 2, so this is around 2 if d is large. Okay, so that means we required n up to 2 the number of parameters. So you can see we have the separation between the standard generation and also robust generation because we require more parameters. Okay.
What is upper bound? Like,
Yeah.
the upper bound is gap of the excess risk.
Yes, the upper bound means this from this is upper bound.
Oh,
Okay. Okay. So okay, this is about the proof. I think I don't need to mention this too much. Okay. Okay. The last question is okay, is this construction optimal or not? Okay. So here we also give the lower bound about the robust generation error. Okay. And we can see that, okay, the robust, the excess risk can also to be found by 2 terms, okay. And we can see that the second term is about the target function, but this is about the robust target function. And also the standard, the clean, the target function. We can see that, okay, it's on the robust generation error and also on the clean generation error. So that means this is data independent, right? It's only care about, this only focus on the target function. Okay. So that means this will only depend on the certain distribution for the F row. Sorry, based on certain distribution row. Okay. Okay. And this results we can match it if the delta is in this is large. But it's true that if delta is, if you remember, we to take this condition is here. It's true that this construction is that the upper bound and lower bounds are not didn't match, but for classification, yes, this is optimal. So the lower bounds and upper bounds they matches each other. Okay, but I will not talk about the classification because I think even though for the regression, I think I have already to take about around 55 minutes. Okay.
So, yeah, I didn't get it. So does it also tell to get the error, you need that many parameters. So you cannot do with less parameters. Is there something you said?
I see that in this case, okay, if delta satisfies this condition, the upper bounds and the lower bounds matches to each other.
Two bounds what? The excess.
Yes.
Yeah, one so with that construction, but I'm saying if I give you like a excess risk,
Okay.
I want to achieve.
Yes.
Do we know that you need at least that many parameters?
Yes, exactly. Okay, so this is what I say the contraction is optimal. Yeah. Because for the standard generation, if you remember, I see that this can achieve the optimal the conversion rates for any the learning algorithms. Okay. Okay. So, okay, so if you are interested in the classification results, so you can check our archive. I think we post, yeah, on January. Okay. Okay, thanks. This is my today's talk. Okay. So, any questions? Okay. Okay.
So, let's imagine you redid this whole analysis with just an arbitrary kernel, right? Like kernel methods instead of neural networks, and trying to find how many parameters you need for generalization with a kernel method.
Yes.
Is there some kind of gap that you can show us showing that, like, neural networks need less parameters, and somehow can always do better than kernel methods? Like, why? Yeah, do you have any insight on that? Or
I think even though we don't consider the robust the generation or the adversarial training, even though for standard training, the EIM, I think there are a lot of work to show the separation between kernel methods and neural networks to show that neural networks work from by the leaf complexity by the RBS result. They show that okay, for example, there are two functions. I can do show that. One is x1, x2, x3, x4. So this is a sparse polynomial. Okay. If we use kernel methods and neural network to learn this function, they have the same as the sample complexity, even though because this is a smooth polynomial. Okay. But if we consider another function from x1, x1, x2, x1, x2, x2, 3, also x1, x2, x4. Okay. So this function have the same smoothness level as the first function. Okay. But the difference is this function is in a sequential way.
like hierarchy.
Yes, okay. Yes.
But so my question is, like, if you consider the same function space, like
Yes.
older smooth functions.
Yes.
Do you see some kind of gap when you're trying to approximate functions for those?
Yeah. Because for kernel method, even though we just approximate a ReLU, this Lipschitz continuous function is actually a special case of a Holder space. The requires the number of the parameters, or if you consider generation, that means the required sample complexity is at least the exponential order of input dimension D. But for Holder space, for the deep neural networks, the rate is 2 alpha or alpha plus D, right? Okay.
Okay, so for this function space, neural networks are clearly better.
Yeah.
Okay, cool.
Okay. 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 Go ahead.
So I know that you're doing an optimization class.
Yes.
So I'm just wondering whether you can carefully confirm whether there are any algorithms that capture the upper bound or just the rate of the excess.
I think if we do the empirical validation, I think this can definitely satisfy this. Okay, because so we can directly construct the neural network, or this is you can regard this as our estimator. It will based on the function. This is you can regard this as our target function. Okay, so you can see this is directly based on the target function. There is no optimization from an error or blah blah. Okay, so this will definitely to satisfy our the upper bounds and lower bounds. Yeah. Okay. But it's true that if we involve with the optimization analysis, maybe we can only focus on 2 neural networks. Okay. Yeah. Okay.
So, given that you assumed this smoothness,
Yes.
how would it change and known of the optimization and so on? How would the result change if instead of ReLU you had sigmoid or tanh that are somehow better behaved, at least in this part?
It can be understand from the alpha by alpha, right? From this is alpha, right? For ReLU, the alpha is definitely smaller, right? For sigmoid or tanh is definitely larger. So you can just say the rates will be different. And then
Like alpha is both in the numerator and like it's both, right? It's 2 alpha divided by 2 alpha.
But you can defeat it by this, right?
Yeah.
Right. So if alpha is large, this is small, this is large.
So the question is, what's the rate, like so you are saying it will be worse?
Yes,
tanh.
No, tanh is better because this is the increasing function of alpha. Right. So if you consider the tanh or sigmoid, this is definitely have a larger alpha. So the rates will be faster. So that means you require less sample can learn it. Okay. Okay.
How do you modify the alpha form?
So empirically, we can do this way, but this way is also very related to how do you estimate the Lipschitz constants of neural networks. Yeah, there are a lot of ways to do this, but sometimes I just to give some approximation to this. Yeah, yeah. So yeah, okay. Okay.
Just want to make it clear.
Mm.
So we want to show that if you perturb the data set to a little bit of to delta,
Yes.
then you can use a lot of parameters to create a large neural network so that you can differentiate these two or separate these two data sets.
Yes.
And you want to show that even though you have a lot of parameters, your neural network doesn't really overfit to the
Yes.
data.
Yes.
So how do you measure like the overfitting phenomenon? Like how can you ensure that your model doesn't really overfit to the data points? Is that like the upper bound on the excess?
Our result can show that okay, it can have the zero training error on the training data on the adversarial training data. So that means it can overfit it. It can overfit it. Sorry, it can overfit on the adversarial training data. Okay.
But can you prevent overfitting on the training data? Because like you want to if you want to differentiate those little the data set that has only a little bit difference.
In practice, normally I think we still want to overfit the data. Because you can see if we don't overfit the data, actually the error will be still very large, right? Yeah. But it's true that so you can see, yeah, we don't want to overfit the data. Maybe the robust generation error would be better. So this is why they call it robust overfitting.
Okay.
Yeah, yeah. Okay. Reverse. This is your turn. Okay.
I guess that's it. Does anybody has any last questions? No? Okay. Let's thank Fanghui one more time.
Okay. Thanks, you guys. Okay.
Yeah.
Okay.反正我正好下个月要